So in this module, let's introduce a very interesting mathematical character, the del operator. And we've done all the groundwork needed for us to at least motivate the use of this del operator. And you'll see that it's a very, very handy symbol and an operator which pervades pretty much all of vector calculus. So it's good to be familiar with it. So in the previous modules, we've already done a bit of work in capturing the total change in the temperature field, right? As you move from one point, say x, y, z, to a neighboring point x plus dx, comma y plus dy, comma z plus dz. And the way we express this total change in the temperature field in terms of the partial derivatives was tau t, tau x dx plus tau t, tau y dy plus tau t, tau z dz, right? Now, what is it that we were doing here? The analogy we had in mind was that let's say we have an air conditioning unit or a heating unit in a room. Maybe it's located at one corner of the room. And as you move around the room, you measure the temperature, you'll see that the temperature changes. And if you move from one location, x, y, z, perhaps let me just draw the Cartesian coordinates. So we have the x coordinate, we have the y coordinate, and we have the z coordinate. So let's say we move from the point x, comma y, comma z to a neighboring point like this, which we label as x plus dx, comma y plus dy, comma z plus dz. Notice that we can connect these neighboring points using a tiny vector, which I've drawn with a red arrow, right? So that's the tail and that's the head of the vector. And this vector can be expressed, if you recall the vector notation, which you may have done in school, the tiny vector can be written as dr, which is dx I, where I hat is a unit vector in the x direction, plus dy j hat, the unit vector in the y direction, plus dz k hat, that's the unit vector in the k direction or in the z direction. Now, if I look at this expression and sort of maybe squint my eyes a little bit like this, you might be tempted to define a new kind of a vector, a new kind of a vector and a new kind of an operator. And the reason we're calling it an operator will become clear just in a moment. But we can define a new kind of a vector which might look like del t, which I'll express in the form only of these partial derivatives. Okay, so I'm going to write del t, where del is what we call the del operator. That's the character that I've been sort of telling you about. That's the del operator. The reason it's an operator is because it doesn't stand alone. It's always operating on some kind of a field, or it's operating on some kind of a vector, some kind of a function. So in this case, the function is the temperature field, which is defined at each of the XYZ coordinates, and del is operating on it. The reason it's operating, it's because it's composed of partial derivatives, right? But I'm just going to write del t for now, and del t can be expressed in the form tau t, tau x, I, plus tau t, tau y, j, plus tau t, tau z, k. And if you look at this expression, tau t, and if I take the dot product of this expression with dr, that's the position vector connecting xyz to x plus dx, comma y plus dy, comma z plus dz, and if I take the dot product of these two, which is del t dot dr, notice what will happen. So I have dx and tau t, tau x. Both of them are in the x direction. They have I hat. And if I dot those two, I'll get tau t, tau x times tx. Whereas the dot product of this expression with any of the other two, since they're coming from orthogonal directions, that'll just be 0. So if I take the dot product of this del t with del dr, I'll end up getting tau t, tau x dx plus tau t, tau y dy plus tau t, tau z dz. And that's nothing but the total change in the temperature field as I move from the point xyz to the neighboring point x plus dx, comma y plus dy, comma z plus dz. This operator, del, which operates on the temperature field, can actually be written in the form, or I can actually maybe just define it and write it in a form tau dx I plus tau dy j plus tau dz k. And it's just composed of partial derivatives, not yet acting on anything. but just composed of the partial derivative operations in each of the three different Cartesian directions. And when it operates, say on the temperature field, tau T, it operates in a manner where this gets operated on the temperature field, and this temperature sort of field goes in, and we take the partial derivative of the temperature field with respect to each of these directions. So then you end up getting tau T, tau X, I plus tau T, tau Y, J plus tau T, tau Z, K. So that's sort of the del operator. And one of the things that it has allowed us to do for now is to just express the total change in the temperature field, which is a scalar field, in a very, very terse notation, which is you take you take the del operator operated on the temperature field and just take the dot product of this with the position vector connecting the neighboring points across which you want to measure the change in the temperature field. So we're going to talk a lot more about this del operator, how it's used. I've sort of very subtly introduced or thought about del as a vector operator. It's not very obvious why it should be a vector. So we're going to explore this idea also in a future video. But for now, we just think of it as a definition where we define this as the del operator, and we'll see where all and how it's used in future videos. Thanks for watching.